So if I draw a line here, and I'm just going to draw some random line in some random direction like this. Let's draw something kind of like this. So here's a line. It's not very straight. I get that. You know, you try to give me a little bit of a break here. Now, it takes at least 2 points to define a line, to draw the line through there. So I'm going to draw 2 points. Of course, there's infinite number of points on the line, but I'm only drawing 2 of them. Now, these points have x, y coordinate values. Now, there are numbers for this coordinate, but I don't know what they are here, so I'm just going to write down that whatever point this is, it has some x coordinate, we'll call it x sub 1, comma, and it's going to have some y coordinate, y sub 1. Now, the reason I have a number 1 here is because I have point number 2 here, and this is going to be x sub 2, comma, y sub 2. So don't get so scared. You know, when I was younger, I used to get scared about the little numbers by the variables. That just is there so that you don't get confused. This point has an xy coordinate pair, x comma y. This point has an xy coordinate pair, x comma y. But we don't want to get confused, so we say this is point number 1, x1 comma y1, whatever the numbers are. And this is point number 2, x2 comma y2. But don't forget that these points are just numbers. They have coordinates that are numbers. All right. Now, what are we trying to do? We just said that if the line is totally flat, the slope has to be 0 because it's not rising at all. But as the line gets steeper, the slope goes up because it's rising a lot. So clearly the rise of the line has a lot to do with how steep it is, and it is. But also, don't forget that when we're looking at a line here, we're trying to measure the slope. We're trying to see how fast does it go up in the rise and compare that to how far it goes over in the horizontal direction to the run. Because this is a line here, right, which is, you know, I would say moderate steepness. But a line that's much steeper like this is much more steep, right? So this is what we would call lower slope. I mean, it still has a slope, but it's lower than this one, and this is higher slope. Why? How do you know this? By just looking at it. Well, you know it because this thing rises a whole lot faster, and it doesn't go over to the right very far. It rises a lot compared to how much it runs. And this one rises, you know, the same amount, but it runs a whole lot more. So basically, the slope of a line depends on how fast it goes up in the rise, and also compared to how far it goes over in the run. Both of them are important. How fast does it go up compared to how fast does it go over to the right? So the slope of a line, for your drum roll here, which in math we use the letter m for the slope of a line. There's historical reasons why we use the letter m. I don't want to go into them right now, but the letter m we don't really use for any other variables usually but slope. So when you see m, it means slope. You would think that we would use s. I get it. It's not very convenient, but we don't use s. We use m for slope. So the slope of a line m is equal to how much does the line rise? In other words, how much does it go up? Compared to, that's why we put a division bar here, in a ratio with how far does it run over to the right, right? So if you want to think about it in terms of directions, how far does it rise up? That's an up arrow. Compared to how far does it go over, right? That's the run. So rise means up, run means over. So you see, this line goes up really, really, really fast, and it goes over to the right very, very little. Rise is big, run is small. So when you divide them, you get a big number for slope. But this one, the rise is this much, and the run is about the same. The rise and the run are about the same. So this, when you divide them, you're going to get a slightly lower number for the slope. So this is what we wrote down. This should be a lower slope. This should be a higher slope. If you ever get down to the point where it's totally flat, then the slope should be exactly 0. We'll talk about that a little bit in a minute. So how do we, let me rewrite this, rise over run. How do we write or calculate how fast the line goes up? Well, when you look at the line we have here, we have these points here. The distance between these 2 points, only that it goes up, is this distance right here. So you can kind of think about it being like this. This vertical distance is what I want. So ignore everything else. How do I figure out the vertical distance between this and this point here? That would be how high the line is rising between these 2 points. Well, this is the y coordinate here, and this is the y coordinate of this point. So how far it goes up is just the difference in the y coordinates, because remember x comma y, the y coordinate is how far the point is up anyway. If you subtract the y coordinates, that's just telling you how far up it goes between the points. So the rise here is point number 2's y value minus point number 1's y value. The difference, y2 minus y1, that's the distance there. And the distance over, which would be this dimension right here, is the difference in the x coordinates. That's how far it goes over, x2 minus x1. And this, ladies and gentlemen, is the famous slope formula. And I know it's not too much to look at and it looks scary. I promise it won't be scary. I'll make it very simple for you to understand and to calculate. We'll do a lot of problems here. But I want you to just take a deep breath and realize what you've done. You now understand conceptually what it is. You have 2 points on the line. You want to figure out the slope of the line, which depends on how far it goes up compared to how far it goes over. Rise over run, right? To find the rise part of it, you just subtract the y numbers of the points, of the 2 different points on the line. And to figure out how far it goes over, you subtract the x values, because that's how far it's going over to the right. y2 minus y1 divided by x2, y2 minus y1 divided by x2 minus x1. Rise over run. Now, for our first problem, it's time to take the training wheels off and actually do something. Here we have the some data that is, it could be anything. It could be how far a bumblebee flies in how far a bumblebee flies compared to how many seconds we're looking at the clock here. So at 0 seconds, the bumblebee is right where at the starting point, 0 centimeters from wherever we're measuring from. After 1 second, the bumblebee is now 3 centimeters away. After 2 seconds, the bumblebee is 6 centimeters away. And after 3 seconds, the bumblebee is 9 centimeters away. So you have a table of values. Literally, you go out there, you could measure bumblebees, you can measure a train, you can measure a spaceship. And what we want to do is figure out basically how fast this thing is flying away from us. How do we compare the slope of the line of these points? When we plot them, what does it look like? So you can see that this data forms xy values, right? You could kind of go over here and say, well, this is 0, 0. And this one, the x value is 1 second, 3 centimeters away, like this. And then we at 2 seconds, we're at 6 centimeters away. And at 3 seconds, we're at now 9 centimeters away. So we put it in a table, but you can just kind of boil it down to your points, x, y points, and now we want to plot these points. So for the first problem, I'll plot them, but after that, I won't plot them anymore. So here we're at 0, 0. So here we have a blank coordinate system here. So 0, 0 is x is 0, y is 0. And then we have 1, 3. So that's 1 for x and 3 for y, which means the next point is right here. And then we're at 2, 6, so 2 for x, which is time, and 6 for y in distance, which is like this. And then finally 3, 9. 3 for time and 9 for distance here. And if you got a straight edge, you could go and see that this does form a straight line. What does it mean, by the way? It means that this bumblebee is not speeding up or slowing down. He is flying at a very constant speed, because every second that clicks by, he goes the same distance away from the previous point. Notice, after 1 second, he goes this far. After 1 more second, he goes the same distance away. After another second, he goes the same distance away. If the bumblebee were speeding up, then this thing wouldn't look like a straight line. It would look like some curved path, which is what we have to use calculus for, you see? That's what I'm trying to tell you. In real life, everything is speeding up, slowing down. Orbits of the planets, rockets that launch into space, any process in engineering really and truly is changing all the time. But what we do is we learn how to handle situations where it's not changing, where everything is just the same pace. I mean, it's changing. His position is changing. It's just the same change every single second. That's what I mean, right? We learn how to find the slope of this, and then in calculus later, when we have everything changing, we apply this idea to find, to have tools in calculus to handle more complex situations. But this is the foundation. So let's take a look at a prettier version of this. These points are all the same. 0, 0, 1, 3, 2, 6, 3, 9. This is the exact same set of points that I drew on my graph. You see it goes right through there. But this is a prettier graph of it right here. Now, how do we find the slope of this line? We know that the slope can't be 0 because if it was 0, it would be a flat line like this, no slope at all. We know that the slope cannot be infinity because if it's a straight up vertical line, I'm going to show you in a little while why, but if the line ever gets totally horizontal, or sorry, vertical, the slope approaches infinity, it's going to be somewhere between there. So how do we find the slope? M is equal to the rise over the run. Now I'm going to write this equation down again, but after a while you don't really need to write it anymore. You'll see why in a second. It's y2 minus y1 over x2 minus x1. All we're doing is we're calculating how far does this line go up. And to do that, we're subtracting the y values of points. Now here's the thing you need to remember. When you have a straight line, it doesn't matter which points you pick on the line. Any 2 points, when you calculate the slope, will give you the same answer. Because the slope of this line never changes. The slope is just a number and it never changes. It doesn't matter which 2 points you pick. And it also doesn't matter which point is point number 1 and point number 2. You're always going to get the same answer for the slope. I'm going to calculate it probably 3 different ways just right here to show you that. All right, so let's just make it easy. Let's pick the first 2 points, these points. We're trying to figure out the rise. How far does it go up here? Well, that's y2 minus y1. We're going to call this point number 2. So we'll take the y value, this is y2 here, 3, minus the y value of this point, 0. The subtraction here is just telling me how far am I going up. Notice it's 3 units higher, and we're going to get 3 units of rise right here. Right? On the bottom, we have to calculate, again, 1 minus 0, the subtraction x2 minus x1. So it's going to be 1 minus 0. Now, the one gotcha that you have to be careful about when you calculate slope is that whatever direction you do the subtraction, y2 minus y1, you have to do the same direction of subtraction for the y point, the y coordinate and the x coordinate. So here I'm basically saying this is point number 2, so it's 3 minus 0, and then this has to be 1 minus 0. You have to do the subtraction in the same direction. Now what do we get? 3 minus 0 is 3, and 1 minus 0 is 1, and so the slope is 3. So I'm going to circle this. Now, what did we get the correct answer? Well, we said that the slope of a horizontal line is 0, and the slope of a vertical line is approaching infinity. And this is somewhere in between 0 and infinity, so it kind of makes sense. Now, what does it physically mean that we found the slope of 3? If you think of the number 3, it can be written as 3 over 1, right? The fraction 3 over 1. And what it means is that this line rises 3 units for every 1 unit of horizontal run. What it means is if I start at any point, this line goes up 3 units for every over 1 unit. Up 3 units for every over 1 unit, up 3 units for every over 1 unit, and you can trace that line out forever and ever because you know the slope of it, it tells you how far the line goes up compared to how far the line goes over. And you can stair step like that forever and ever and trace the whole line out because once you know the slope and you know one point on the line, then you can just find any other point you want. Go rise and overrun, rise over run, rise over run, and you can continue tracing the line out. Okay. So let me do something a little goofy here. Let's calculate the same thing again. y2 minus y1, x2, x1. Now, here in this case, we basically said, all right, this is point number 2. So we did 3 minus 0, 1 minus 0. We basically said this is point number 2, y2 minus y1, but let's flip it around. Let's say this is point 2. So it doesn't matter the order in which you do it. Let's subtract the other way. We'll subtract the y value 0 minus 3. This would be if this was point number 2 and this was point number 1. So 0 minus 3. These are the subtraction of the y points in reverse order, assuming this is point 2 and this is point 1. And then we have to go the same direction, 0 minus 1. You see, we did the same math. It's just that because we did it in a different order, because we basically flipped which one was the x, which one was point number 2 and which is point number 1, the subtractions are totally backwards, but they're the same. They're the same direction. No matter, you know, the fact that they're in reverse order, we still subtracted the same direction in this one. So 0 minus 3 is negative 3, and 0 minus 1 is negative 1. And what is a negative divided by negative? It's a positive 3, and you get exactly the same answer. So whatever points you pick, all you have to do is subtract the y values and then subtract the x values, but you have to go the same direction, and it doesn't matter which one you consider to be point number 2 and point number 1. You will get the same slope. Now let's go on and calculate the slope a couple of different ways with different points. Let's go and find the slope using 2 other points. Let's choose these points here, right here. And let's consider this to be point number 2 and this to be point number 1. So it's going to be 9 minus 3. Again, I can write the y2 and all that again, but really all you have to do is rise over run, subtract the y values, 9 minus 3. And then we have to subtract the same direction, 3 minus 1 for the x values. It's just 2 subtractions, guys. It's not that hard. I know this looks confusing, but just remember, subtract the y values, subtract the x values, go the same direction. 9 minus 3 is 6, and 3 minus 1 is 3, and 6 divided by 3, sorry, if I could subtract correctly, I'd get the right answer. 3 minus 1 is 2. 6 divided by 2 is 3, same exact slope that we calculated here. So here we found the slope of this line, and we got the same answer using 2 totally different points. Now let's do it one last time. Let's use these interior 2 points, but let's not pick this as point 2. Let's pick this as point 2, so we'll subtract this way. 3 minus 6 for the y value. 3 minus 6 for the y2 minus my 1. We have to go the same direction, 1 minus 2. So we're subtracting this way for y, this way for x, 1 minus 2. 3 minus 6 is actually negative 3, and 1 minus 2 is negative 1. Negative divided by negative is positive, and we get a 3. So I'm trying to show you by example that when you have a line, that line has a slope, and that slope is the same. You will always get the same value for the slope, no matter what 2 points you choose to put into the slope formula. And also, even if you reverse the points and consider, it doesn't matter which one is point 1 and point 2, as long as you subtract the y values and the x values in the same direction, no matter what 2 points you pick, you should always get the same value for the slope, because that's what a line is. It's a set of points that are connected that have the same relationship of rise over run between those points. So that's why we can go up 3 over 1, 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 rise over 1, rise over run, up 3 over 1. That's where I started the journey. I said, here you have some points. You have point number 1, point number 2, rise over run, up compared to over. It's a ratio of how much the line goes up compared to how much the line goes over, and this is the slope equation. So let's take this down. We have a couple more problems, and then we'll wrap up this lesson. One important thing I forgot to mention here before I wrap up this last problem, here was the slope of that line. The answer that we actually got was a slope of what? Of 3. But what are the units of the slope, and what does it actually mean? Notice that when we find the slope, we're taking the rise, and we're dividing it by the run. Right? And when we did the rise, we figured out that it rises 3 units up, because we subtract 3 minus 0, we got 3, and then it was 1 minus 0 on the bottom, and we got a run here. But this 3 here, when we subtracted the 3, we were subtracting centimeters. So it was 3 minus 0 centimeters. So this thing traveled 3 centimeters up for every 1 second to the right. So when we take 3 divided by 1, we get 3, but the units left over are centimeters per second. So when you find the slope, it's always going to be some kind of unit that you're familiar with. You know, when you're driving a car, it's kilometers per hour. When you're, a spaceship might be in thousands of kilometers per hour, thousands of kilometers per second even, right? So when you have a rise divided by a run, it's some unit divided by some unit. So what you're going to get is some kind of rate. That's what you're going to get. So here it's 3 centimeters per second. And just like I said, that this tells you the line goes up 3 units up for every 1 unit over. What it's also telling you is that this bumblebee, or whatever it is traveling 3 centimeters every second. 3 more centimeters every second. 3 more centimeters every second, because every time I go over, it's 1 second, and I'm going 3 centimeters every second. That's why the unit is 3 centimeters per second. I want you to start thinking about units as we do this stuff as well. All right, for problem number 2, let's take a look. Here we have, this could be the distance traveled by some person walking, right? So here, after 1 hour, I travel 1 kilometer. After 2 hours, I'm at a distance of 3 kilometers from the starting point. So I guess after 1 hour, I'm 1 kilometer away. After 2 hours, I'm 3 kilometers away. After 3 hours, I'm 5 kilometers away, and so on. So we can make these into x, y points. So here we have 1, 1. This is 2, 3. But don't forget what the numbers represent. This is distance and time, right? 3, 5, and then 4, 7, and then finally 5, 9. Right, so we can plot these points. Now in the last lesson I plotted them all and all this, but I'm just going to skip that part. And I think you can recognize here that 1, 1 is here at x is 1, y is 1. 2, 3 is x is 2, y is 3, and so on. And I can take these points 3, 5, 3, 5, and then 4, 7 was the next point, and then 5, 9 was the final point that we had. So this actually forms a line as well, a straight line up and to the right. But if you remember, compared to the last problem, it's not quite as steep. This one is actually steeper. If you can just kind of hold this in your mind, this one was very steep with a slope of 3, but this one doesn't look quite as steep. It looks to me to be a little bit more flattened. So we expect the slope to be less than 3, because if it's flat, the slope is 0, the slope gets bigger, 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 bigger. This is this line right here, and the one that we got before was actually even steeper. So that was a slope of 3. This slope should be less than 3. So let's calculate what that slope is. It's rise over run. And I'm going to write the slope equation down, but we're not going to have to use it too much. It's the subtraction of any two y values, which is the rise, compared to or divided by the subtraction of any two x values, which is what we call the run. Now you're free to choose any 2 points you wish, and also any order in which you wish. So let's just pick, I don't know, this one for point number 2 and this one. So we'll choose these 2 points. I'm literally just picking them randomly. We're going to subtract y2 minus y1. We're going to choose this to be point 2 and this to be point 1. So 9 minus 3. That's how far this line goes up between these 2 points, 9 minus 3. Right? And then we have, if we're going to subtract 9 minus 3 this direction, we must subtract the same way, 5 minus 2. We have to go the same way, 5 minus 2. All right, what is 9 minus 3? It is 4. What is 5 minus 2? It is 2. And so 4 divided by 2 is 2. And what are the units? Well, this was 9 minus 3. This was subtracting kilometers. This is kilometers. And this is hours. So the rise, when we subtracted the y values, was subtracting kilometers. Here we're subtracting hours. So it's kilometers on the top and hours on the bottom. So what it's saying is that you're walking at a speed of 2 kilometers every single hour. So we'll put a slope here of 2 kilometers per hour. That's just the slope of that line. Let's see if it makes sense. Okay, I start here. After I go up 2 kilometers for the next 1 hour, because notice the difference here is 2, and I will over 1 hour. Up 2 more kilometers in the next hour, 2 more kilometers in the next hour, 2 more kilometers in the next hour. Because the number 2 is the same as 2 over 1. That means a rise of 2 compared to a run of 1. Up 2 over 1, up 2 over 1, up 2 over 1, 2 kilometers for every 1 hour. That's what that means. Now, I'm not going to do it a million different ways, but let's go ahead and calculate it a different way using different points. The last time we used these points. Now, instead of that, let's use these points. And let's not choose this to be point 2. Let's pick this one down here to be point 2. So we'll subtract 1 minus 7 on the top. So it's y2 minus y1, x2 minus x1. But we don't need this equation. We just need to subtract the y values. And we're going to subtract 1 minus 7. We're going to go backwards. 1 minus 7 on the top. And if we're subtracting this direction, then for the x-coordinate, we must subtract the same direction, 1 minus 4. Now, 1 minus 7 is actually negative 6, and 1 minus 4 is negative 3. Now, negative divided by negative is positive, 6 divided by 3 is 2, and so the answer is 2. It's exactly the same slope that we got before. So for this calculation of the slope, we not only chose two totally different points on the line, but we reversed the order of them, and we made the bottom point number 2, so we subtracted that way, and we just had to be consistent in the way we subtracted. We always should get the same value of the slope. This is how far it's going up, 2 units for every 1 unit over, because this can be written as 2 over 1. And when you attach units to it, it's 2, in this case, kilometers per hour. All right? And notice that the slope that we got of a 2 was indeed smaller number than the slope of this line, and that is because this is a very steep line, and this is a little more shallow. If the line gets closer to 0, then the slope is exactly 0 when it's horizontal. All right, I'm going to take this down. I really want you to pay attention to the next problem because we have to show you the concept of what a negative slope is and how you can actually have a negative slope in this calculation. I promise it's not hard, so we'll take this down and we'll do our last problem. All right, here is problem number 3. It's an interesting problem. I want you to think about it. This is the water level like in a swimming pool or in some kind of container or just even a cup of water outside or something like this. So on day number 1, we have 9 millimeters of water in this thing. So we have some water out here, and then the water level here is at, the distance, the water level here is at like 9 millimeters or something like this, okay? But then on day number 3, so you skip a day, day number 3, we actually only have 7 millimeters of water in this cup. So the water level went down. But then on day number 5, we only have 5 millimeters of water. So the water level went down even more. You see what's happening? The water's evaporating. So the water level is going down, 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 down. In the previous 2 problems, when we were doing distance, the problems were chosen so that as time goes on, we're going farther away, we're driving down the road. But this one's a little different because as time goes on, the distance number is getting smaller, not bigger. So for instance, this point x comma y is 1 day, 9 millimeters. This is 3, 7. This is 5, 5. This is 6, 4. And this is 9, 1. Like this. Notice what's happening. As time goes on, because the first number here is time goes on, the water level is going down. So when we plot these points, what does it look like? The line is reversed in direction, whereas all of the other lines were kind of going this way. This line is flipped over and going totally opposite direction because when time is 1 day here, 1, 9, the point is here. But on day number 3, we've gone down to 7 millimeters. On day number 5, we've gone down to 5 millimeters. On day number 6, we're at 4 millimeters. On day number 9, we're at 1 millimeter. Forgot to close in parentheses right there. So you can see that this one is different than the previous problems because as time goes on, the numbers of whatever it is we're measuring are going down instead of up. And that is going to be reflected in the slope. When the slope is going down, down, down like this, the slope ends up being negative. It still represents the same thing. Higher slope lines are bigger numbers, but they're going to be negative numbers. Any line that slopes this direction is going to give you a negative slope, and any line that slopes in the other way is going to give you a positive slope. But the representation of what it means is still the same thing. The magnitude of that number, the number itself, tells you how steep that line is. All right, so let's calculate the slope of this line. So it's rise over run, y2 minus y1, x2 minus x1. Okay, you don't have to worry about if it's negative or positive. Just pick 2 points on the line. Let's just pick easy points, these 2. Let's figure it out. Which one is point number 1? Which one's point number 2? I don't care. We can do whatever way you want. Let's say this is point 2 and this is point 1. So we'll subtract the y values. 4 minus 1. And then if we subtract it this way, we have to subtract the x values the same way. 6 minus 9 is what we have to do. Now, what is 4 minus 1? That's 3. And what is 6 minus 9? That's actually negative 3. But when we subtracted these y values here, 4 minus 1, we were subtracting water level, and that was in millimeters. I guess I could label this as millimeters, and this is time in days. So when we subtracted the y2 minus y1, 4 minus 1, we were subtracting millimeters. So this distance we got here was in a difference of millimeters. And when we subtracted the time here, it was in days. So what is 3 divided by negative 3? That's negative 1. And what are the units left over? Millimeters. Whoops, if I can write millimeters. Per day. Now, what does this mean? This is telling you exactly what you expect it to tell you. The water level is not rising every day because the actual slope is negative. It's telling you that you're losing 1 millimeter every day. You're going down 1 millimeter a day. The negative sign on the slope is telling you 2 things. It's telling you physically the numbers are going down over time. That's what the negative sign is. And it's also telling you that if you plot it, the slope is slanted the other way. Negative slope lines that look like this have negative slopes. Lines that look like this always have positive slopes. And so the answer that we get is -1 millimeter per day. Now, let's think about this a little bit further. Any number you can write as, in this case, -1, you can write it over 1, right? Any number is itself over 1. So we can think of it as rise over run, right? Because this is what we did. This was the rise. We calculated it, and this was the run. We calculated it. So when we get our answer, the rise is -1, the run is 1. Right? So what does it mean to rise negatively? You know, I told you before, rise up, over, rise up, over. But here we're saying the rise is actually negative. That means if you start at any point, you rise down 1 point, and then you go over to the right 1, down, over, down, over, down, over, down, over. So when the slope is negative, it's telling you rise over run is negative, which means you actually rise down instead of up, and then you go over. That's why the line is flipped the other way, because when the line is going this way like this, then if you have a positive slope, you rise up a positive number and then over, and then up positive number and then over, and then up a positive number and then over like this. But when the slope is negative, it means you actually end up rising down. So you rise down 1, and then, because the number is 1, and then you go over 1. Down, rise down, and then over to the right. Rise down, and then over to the right. Rise down, and then over to the right. And then that means that the line is flipped in this direction. Now, the last thing I'll do for this one is we'll calculate the slope one last time, and we'll just verify that we get the same answer, because that's really, really important. So for the last time we use these two numbers, let's do something crazy and use like these two numbers, but let's also flip it around and basically say this is going to be 0.2 and this is going to be 0.1, right? So what we're going to do is say 5 minus 9, because we have to subtract the y values, 5 minus 9. And if we do it this way, then we subtract the x values same way, 5 minus 1. Right, 5 minus 9, that's -4, and 5 minus 1 is +4, and then 4 divided by 4 is 1, and because of the negative sign, it's -1, and we get exactly the same slope that we calculated before, -1 millimeters per day. So I do have a couple more things I want to talk to you about in this lesson. But before we get to those things, to wrap up everything, I want to impress upon you the most important things. When you calculate the slope, you are figuring out how steep that line is. And the bigger the value of slope, the steeper the line. All right? If the slope ends up working out to be 0, it means your line is totally flat. If your line works out to have a slope of infinity, it means it's a vertical line like this. But any other slope in the middle is going to tell you, relatively speaking, how steep it is. The bigger the number it is, the how steep it is. The bigger the slope, then the more vertical the line is. But if the line tips the other way, so you get over here to like infinity slope, if it tips the other way like this one, then the slope flips around and turns negative. Because then rise over run is negative, and you're rising down over, down over, down over. But the same representation applies. It's just telling you that the line is going down with time instead of up with time. So instead of walking and getting farther away, like in our first two problems, bigger numbers with time, here we're getting smaller numbers of time. So our slope of -1 millimeters per day is telling us that we're losing 1 millimeter every single day, because we're going down 1 millimeter for every single day. That's what it means. Now, I want to do a couple more things before we close. Those were our actual problems, but I've been saying this a lot, so I want to make sure you understand. Let's take a couple of special cases. Let's say I have a horizontal line. What would be the points on the horizontal line? Let's say this is 1, 3, and let's say this is at 5, 3. In other words, if you put a grid on here, 1 and you go up 3, and this is 5 and you go up 3. So the points are horizontal like this. The slope is going to be, y2 minus y1, x2, x1. Now, it doesn't matter which way you subtract, so let's do 3 minus 3. And then we have to go the same way, 5 minus 1. Now 3 minus 3 is 0, and 5 minus 1 is 4. Now 0 divided by anything is 0. So this is what I was saying, is that the slope is 0 anytime you have a horizontal line. Why? Because when you find the rise of this thing, because the y values are the same, it doesn't rise at all. So there's no rise. A rise of 0 means there is no slope. It doesn't slope at all. That's point number one I wanted to show you. Point number two is I wanted to show you what happens if the line is completely vertical like this. Let's make up some points that could lie on this line. Let's say this is at like 2, 6, and this is at 2, 9. So it's like over 2, up 6, over 2, up 9. And so it's vertical because why? The x values are the same. That's what makes a vertical line like this. So the slope is the same thing. We subtract the y values. I can go any way I want, 9 minus 6. And then I have to subtract the x values, 2 minus 2. 9 minus 6 is 3. 2 minus 2 is 0, but how do you divide by 0? You can't divide by 0. It's undefined. So in a lot of books, they'll tell you the slope is undefined for that line. But in reality, if you think about what would happen if the line were tilted just a little bit from this, then these would not be exactly the same. They would be very close, but they wouldn't be the same. You would be dividing by not 0, but a very small number. You would get a very, very, very big slope. Okay, so as the line approaches vertical, the slope gets bigger, bigger, bigger because these numbers get close together. You can't really divide by 0, but you can approximate that by basically infinity. When you take 3 and divide by nothing, how many times can nothing go into 3? It can go an infinite number of times. So a lot of people say it's undefined. That's fine. You can think of it that way. Or you can just think of it as infinite slope. So you have a slope of 0 when it's flat. You have a slope of infinity when the line is up and down. And all of these slopes in between are just going to be some number between 0 and infinity. Of course, if the line flips the other way, then the slope is negative. And then the last thing I'm going to leave you with is I promised you at the beginning. I said, hey, this stuff, the slope of a line, really does build the foundation of calculus. And you think, well, he's just kidding. It doesn't really, but it really does. When you go into calculus, the first chapter talks about finding something we learn about in calculus called the derivative. Now, I don't care if you know what the derivative is. It doesn't matter. But the derivative, I'll just tell you in layman's terms, it is a way to figure out the slope of something when it's not a line. So let's say we have the orbit of a planet, for instance, right? Or we could say the launch of a spaceship. When you launch a spaceship, it launches up and then it curves over to try to go into orbit. These are curved paths. Now, this is supposed to be an ellipse. It's not really a good ellipse, but you see the idea. How do we figure out the slope of something like this that's changing? Well, it's very hard because it's always changing. So for a line, it's very simple because the slope is the same. But here, the slope, you can see the slope is very high, but the slope here is very low because it's starting to go horizontal. And it's changing the whole time. So what you do in calculus is you say, all right, forget it. I can't figure out the slope exactly. So what I'll do is I'll just draw a line that just barely touches this curve, and I'll figure out the slope of this line. And then over here, I'll find another line that barely touches this curve. I'll find the slope of this line. And then I'll find another line that barely touches the curve here. So what I'll do is I'll break my curve path into a bunch of tiny little lines. And I'll find the slope of those lines. And I can figure out and do a lot with that. It's called the derivative. You learn it in calculus, and it forms the basis of everything else. In my ellipse, what if I want to figure out the orbit of a planet? They're all elliptical shapes, but it's always changing. How do I do that? Well, I break this thing up into a little line segment. And then from here to here, I break it into a line segment. From here to here, another line segment, line segment, line segment. I can go all the way around this thing, making little line segments. Now, it's an approximation of the oval, but I can make these line segments really, really, really small and get an excellent approximation for what that oval is doing. And I can find the slopes of all these little line segments and make them really, really, really tiny and figure out what this thing is doing. So here we learn the slope of a line. You're going to learn it. We're going to use it. We're going to get comfortable with it. Later on, when you get to calculus, you're going to open up page 1, and it's going to talk. They're not going to tell you the slope of a line. They're going to call it a derivative. But what you're doing is you're breaking up any curved path into an infinite number of little bitty line segments, which we know how to find the slope for. We add them all up, put them all together, and we can analyze complicated shapes. That is why this is so important, because it feeds into that which we use for everything. So please watch this lesson twice. It's that important. Calculate the slope. Follow me on to the next lesson. We'll continue to build your skills. Learn anything at mathandscience.com.